Okay, so let's talk about the microbit and the way we can hack this tiny device. So just to introduce myself, I'm Damien Cauquil, head of R&D at Telecom Digital Security. Sorry. This is a French company. I'm also a senior security researcher, and I'm also a software hardware reverse engineer. So I'm French, expect errors and so on, but I think you're quite familiar with it. So we will talk about the microbit. Microbit, this is a tiny device with many amazing features, many interesting things from a hacker point of view. And I will introduce you to a way to turn the microbit into a sniffer and into some nice tools in order to hack into radio frequency protocols. And I'm going to show some demos too. So first of all, the BBC microbit. So this is a BBC-sponsored device that was given to a lot of students in the United Kingdom in order to facilitate the learning of coding in UK schools. So basically, it has a 5x5 LED screen, LED matrix, 2 buttons, a nice custom expansion connector, and also wireless capabilities. So it's worth to be noted because this is the interesting part in the microbit. And it's running MicroPython, so if you want to code in Python on the microbit, this is possible. It costs only $15. I checked on SparkFun, so if you want to buy one, it's very cheap. From an hardware perspective, this is a device based on the Nordic Semiconductors NRF 51822. It's a bit weird, it's a bit one name, but it's a 2.4 gigahertz GFSK demo transceiver that comes along with the CPU. So it's pretty cool. It has 256 kilobytes of flash, 16 kilobytes of RAM. You can use some pins as ADCs. So if you want to read digital, to read some voltages or so on, you can do it. It also has a SPI bus, I2C bus, and you can use 20 GPIOs to do whatever you want with the expression port. It's powered in 3 volts, so it's kind of cool. You can power it with 2 AAA batteries, so it's very portable and affordable. It's also easy to program. This device has been designed to fit the children's needs. So everything is online. You can use a JavaScript blocks editor, for instance, developed by Microsoft. It's kind of Scratch. You can use to program your microbit. You just put blocks and develop on the microbit by using this editor, or you can do it the Python way by using an online editor. If you put some Python code in it, it compiles online, and you get the next file. You have just to put this file on in your microbit. This is an interesting device because if you plug it through a USB cable to your computer, it pops up as a mass storage device. So you just have to drag and drop your file, and it flashes automatically your microbit. So this is very cool. It also has a REPL, a read evaluate print loop. So if you want to debug your code, you can just use say a minicom, and you can debug it through UART. So this is nice to when you are developing some code on the microbit. And it also has wireless capabilities, and this is the most interesting part. This transceiver, the NRF 51822, is able to communicate through legacy shockburst protocol. So this is a protocol designed by Nordic. And also the enhanced shockburst protocol. This is the new version of this protocol. And last but not least, the Bluetooth low energy protocol. So this chip can emulate devices. You can put some Bluetooth low energy services on it, create a Bluetooth enabled device. So this is great. So when I discovered this capabilities, I was like, So it's interesting because French, I said. It's interesting because the enhanced shock burst protocol is well known as it was presented last year by Mark Newlin from Bastille. And it was attacked by Mark Newlin during this last DEF CON. And it developed what he called the MossJack framework. So the MossJack framework basically is a set of tools able to hijack wireless keyboards and mice. So it's a great tool written in Python too. It's also open source, so it's a good way. So it's good to know the basics of this hack, because it's not Mark Newlin who found out how to turn this device, which is a crazy radio PA here, into a sniffer. All the credits go to Travis Goodspeed with his NRF24L01 Plus hack. In this hack, he managed to turn another chip for a Nordic semiconductor, which is the NRF24L01 Plus, into a sniffer by using a trick I'm going to talk about in another section of this presentation, but it's good to know. Also, Sami Kamkar made this key sweeper, which is a tiny device. It's very small, and it looks like a power adapter. But inside, you find an Arduino connected to an RF24L01, so it's able to sniff wireless keyboards. And it's also using a GSM gateway to send text and receive text, so you can get the intercepted stuff, intercepted keystrokes over wirelessly with your phone. Another interesting tool for 2.4 GHz protocols is a DSMX hijacking tool called Icarus. So this one is a bit weird here, but in fact, this is a tool that uses some kind of sniffing to hack into the DSMX protocol. What is DSMX protocol? It's a protocol used with model airplanes. So when you're just flying model airplanes, you may use a controller and a receiver that uses this protocol. And they hack into this protocol, and we're able to take complete control of, say, a plane or a quadcopter, in this case. So, after having reading all of this, I was thinking about doing some kind of offensive Python on the microbit. You know, maybe it's possible to turn this microbit into a sniffer, and hopefully it is, but maybe we can do a lot more with this. So, just have a look at it. So let's start digging into the microbit, and I'm going to start with the NRF51822 specifications, and especially the way you can turn this transceiver into a sniffer. So I talked about the Travis Goodspeed hack. So this is how the Travis Goodspeed hack works. So basically you have a datagram sent over the air, and the transceiver tries to match some fields just to identify a valid packet. Your packet starts with a preamble, which is in this example 55 in X, then followed by a 3-byte address. So the address can be 3, 4, or 5 bytes when you are dealing with the enhanced shock burst protocol. And this address is followed by a packet control field, which is 9-bit, then a payload, and at the end a CRC. So this is a basic setup for an ESB protocol. But what Travis Goodspeed discovered is that the matching, when the transceiver tries to identify the start of a packet, it does not rely on the preamble byte. It performs the matching of on the address. So if you configure your NRF24L01 in a weird way, there is a possibility to sniff. I mean, since the matching is performed on the address, if we set up the transceiver to match a 2 bytes long address rather than the 3, 4, or 5 bytes, and if we put a 0055 in X as an address, it will match the preamble of the packet. So, we also configure this transceiver to forget about the PCF field. So we go back to the legacy shock burst protocol, and we tell the transceiver that we need 32 bytes of payload. So in the payload, we will find the ESB address, which is here 3 bytes, the 9 bits of the PCF field, the original payload, and also a CRC. In order for this packet to be notified to our code, we need to disable the CRC. Why? Because if the CRC is enabled, the matching algorithm will check the CRC, and in this configuration, the CRC does not match. So once you configure your transceiver this way, you're able to sniff. So this is for the 24L01 plus, not for the 51A22. But basically, they did the same mistake on the 51A22. So if you just tweak a bit the configuration of the 51A22, you can get the exact same effect. There are some differences between the 24L01 plus and the 51A22. So basically, the 51 is able to do both big endian and little endian values, where the NRF 24L01 just sticks with the big endian. And also, the NRF 51A22, that's very difficult to say, sorry, has a payload with a max 254 bytes instead of the 32 bytes we got with the 24L01 plus. So it's very cool because we were limited with the 24L01, but the limitation is no longer here with the 51. But the configuration is a bit more complex. So here how it is done. I put all this on the code. So you have a base 0 and prefix 0 registers. You have to put some 0 in it and 55, just to be sure to match the preamble. We configure the PCF field to be 0, to just, it's a useless field here. And also we set up the Indianness to big with some kind of value, and we set up the maximum payload length to 40. Why 40? Just to be able to catch the 32 bytes payload. We would have missed if we were using the NRF 24L01. Once you set up your 51 and 822 like this, you will get some packets in it because it matches the preamble. But we have to check the CRC ourselves, because this is not performed by the transceiver. So by doing this, and by using some code from NRF Research firmware, which is a firmware used for the MassJack tool, we can check the CRC and just avoid all false positives from this. So I put all of this into a modified MicroPython firmware I've wrote. I will release this at the end of this talk. And modify the Micro and Python radio module just to implement some new features such as this sniffing trick. And by using some lines of Python, I was able to develop a quick ESB sniffer. So I got a little demo to show you how it works. So first of all, I am programming my microbit with my specific firmware. I tell the microbit to use a specific Python file I wrote. So this is the file I showed you just before. And by connecting to the UART with a specific baud rate, I am getting all the stuff printed by the microbit. So here you can see many devices talking with over some kind of ESB protocol. So this is a Logitech wireless mouse, and it's sniffed without any problem by this little hack. So here it is. But we are not limited to ESB protocol or SB protocol. As it's a 2.4 gigahertz transceiver, we can do a lot of stuff. We can do sniffing, also can inject information into this protocol. And this technique is not limited to ESB, so we can hack into any 2.4 gigahertz protocol that relies on a JFSK modulation with a specific data rate. So there is a whole new world of possibilities. And as a fiddle hacker, I obviously own some kind of quadcopter, and I decided to put some support for the XN297 transceiver, which is found in the Tierson CX10. I don't know if you're familiar with this quadcopter, but it's quite a common. So, but the transceiver is not common. This is compatible with our NRF 51822, but there is a slight difference. That is, this transceiver uses a data whitening algorithm. So anyway, it's not a big deal. So I developed a lot of some method for the radio module to keep it to be able to communicate with the XN297. So if you use the custom preamble used by this transceiver, which is 671OF55, as a receiver and transmitter address, you can communicate with this device without no problem at all. So this is a pretty easy to implement in the microbit. Although the NRF51822 is Bluetooth Smart capable. So I was wondering if there were some kind of possibilities to sniff some Bluetooth Smart traffic. And this is possible. And just as a reminder for those here that do not know where the Bluetooth Low Energy Protocol. The BLE protocol uses 3 channels to advertise devices. That is the 37, 38, and 39 channels. These channels are spread along the whole band, 2.4 gigahertz band. So this is just as a reminder. And every device that performs this advertising stuff has to send specific packets to a specific access address. This is a 4-byte address used as a preamble just to match, to identify unique links. And in this packet, you will find some kind of PDU. And this is a PDU that tells BLE stack what's it all about. So here we are looking for advertisement. And I also put all of this in my modified microbit firmware, MicroPython. So I wrote a quick BLE advertisement sniffer using Python, and I ran it yesterday or this night at the hotel. So it's there were a lot of devices advertising themselves on channel 4. This is quite normal. But we can also spoof advertisement packets. So if we build from scratch a packet, we can create a DEFCON 25 device and advertise this device. But furthermore, we can do some fuzzing on the PDU parsers used in many BLE stacks. So I decided to modify just a byte, the first one before the DEFCON 25 string, which normally is 09. But I put a OA, so just a value of +1 instead of a 9, and I advertised this device. And I used my laptop with my integrated BLE adapter just to detect the devices that were around. If you look carefully, you can see that even I sent a malformed PDU, but my stack got it, and I get one more character at the end of DEFCON 25 because it thought that it was a 10 bytes long string rather than a 9 bytes. So can be also useful to test some kind of this stuff on Bluetooth. Furthermore, we can try to sniff BLE connections. So if you want to make a 15 bucks BLE sniffer, well, maybe it's the way. So I tested this. I tried to sniff a BLE connection request. That's the BLE connection request is a specific packet sent by a device that wants to connect to a specific other device, BLE device, to provide this device with all the requested parameters. And we can sniff this connection request. So I did this again with a BLE device I own. So everything is on a microbit still. So it takes some time to get the connection request because since the device advertises itself on 3 channels, you get to be on the right channel when the connection request arrives. Just waiting. Okay, we got the first one. So here we got the access address, which is a 4-byte address identifying the link, and the initiator address, the advertiser address, the CRC in it, which is important here because if you don't have this value, you cannot compute the CRC for every packet, and the hop interval, which is a value that is used to determine the hopping frequency. So obviously, I was on the good start to sniff BLE connections, but in fact, Python cannot do sniffing well with a microbit because MicroPython introduces incompatible delays. It's slow. Just to say it simply, it's slow. We have a few RAM available, so it's very difficult to get to create or to develop a BLE sniffer using this MicroPython stuff. So, but this is not really a problem, as we are going to see later. So I decided to implement some tools. So the first one was a mouse jack-like ESB sniffer, obviously, since I was in the wireless keyboard and mice hijacking. So this sniffer is able to dump 32 bytes payload, whereas the mouse jack original tool cannot. And it supports ESB and legacy ESB, and also the BLE link layer implemented some kind of Bluetooth AD sniffing at the link layer, just to be able to capture packets. This is quite new. It also introduces follow mode for ESB, but this mode is also present in the mouse jack tool, and it can do raw sniffing. This is very useful when you are trying to debugging some 2.4 GHz protocols. So this is the system. I tested my tool against my wireless keyboard and mouse. So again, I programmed my microbit to use some kind of middleware I've developed, and I start my sniffer, telling my sniffer to follow a specific device, which is my wireless keyboard. So you can discover these devices by using the same tool. And here we go. So we get many packets, many acknowledgements, and if I type in with my keyboard, as you can see, you get other packets. So this keyboard sent encrypted frames, so this is not sent in clear text. So this is good. But if I take a notepad, and if I type with my wireless keyboard, so you can see there were a lot of packets sent or exchanged between the wireless keyboard and dongle. So by doing this, we can spy on wireless devices using the ESB protocol. Obviously, it was sounds like a good idea to create a wireless keylogger using this microbit. So I use the microbit with two AAA batteries, and I created the software, so it uses a UART interface to send the recorded keystroke, and the microbit provides a tiny file system you can use to store in memory, in persistent memory, the data. So if you want to get track of every keystroke sniffed by this device, so this is a good way to go. So I decided to plant my keylogger in the meeting room we have at Digital Security. So I just power it on. You can see the LED doing some kind of searching for a wireless keyboard. And I asked a colleague of mine to log into an account using this wireless keyboard. So he is currently logging in Outlook using my vulnerable keyboard. So he's entering his password. There it goes. So everything was sniffed by this keylogger, and when I get my keylogger back, I connect this keylogger to my computer. So this is the raw stuff to get the keystrokes. Okay, so just going a bit faster. So I press a button, and here it is. I get all the keystrokes. So this is the password is Henri Meunier in French with a lead speak. So this is. So it was done with less than 200 lines of Python. The hard part was the HID conversion from the keystrokes to the characters. And sounds nice too to try to hack into some kind of wireless quadcopters 2.4 gigahertz based quadcopters. So I saw in November 2016 that Mark Newlin and challenged Michael Osman and Dominic Spiel during tour camp. The idea came from Mark Newlin. He wanted to make some kind of drone duel against Michael Osman. So they unboxed 2 Cheerson CX-10, and they tried to hack the other's Cheerson. So it was done with the mouse jack framework from Mark Newlin. And I don't know what tools used Michael Osman, but I guess it's SDR-based. And the result was the following. So apparently it ended up with a draw, and no phishing nets or hijacking whatsoever. So that was a good start. Dominic Spiel and Michael Osman presented the CX-10 wireless protocol during the talk camp, so I got all the stuff already done. So this is a binding request sent by the remote controller to the quadcopter. So basically, it's the controller sends a binding request containing its transmitter ID, and the quadcopter answers back with a binding reply with a transmitter ID and a vehicle ID or aircraft ID, and followed by a confirmation. And then they start hopping from channel to channel, sending from the controller all the information about the stick positions from the controller. So basically the throttle, yaw, pitch, roll, and button states. And it does this by looping on different channels. So my idea was to create a RUG controller that would be able to take over an existing connection and to take control of the drone. So this can be done by sending a RUG packet just before the original controller does, and by doing this, we can take control of this. So the channel hopping mechanism is just using 4 channels that are derived from the transmitter ID. So once you got the transmitter ID, you get the channels. So the hijack is quite common. We sniff a valid packet from channel 3 to 18, which is the first range of the first channel used by this drone. Once a valid packet is found, we get the transmitter and vehicle ID. We check this transmitter ID against the channels. We derive again the channel list and check if the channel we are currently listening on is in this list. And if it's okay, we just synchronize with the drone and send quicker. We send packets quicker than the original remote and get control of this. So the radio is set by using my MicroPython modded firmware. So this is the same. We wait for a valid packet, which starts with a 55 and index preamble. We get the transmitter ID, we derive the channels, and we check if the channel we are listening on is in the channel list. If it's okay, if it's found in the channel list, then we start synchronizing with the drone and then send packet with the correct values to take control of the drone. But the fact is, I need a way to to pilot the drone, so I need a remote controller. I thought about using a classic RC, but no, this is way too complex. This is using some kind of protocol. I also thought about using a USB-compatible gamepad we use normally in the model RC, but again, this was very complex. So I decided to go with an existing remote controller from a CX-10. And so I modified my remote controller, put some wires in it, unsoldered the original transmitter used in this controller, and made my own RUG controller. So that's it. With this controller, I have able to read the stick values by using the ADCs from the 51822. And I won't perform any live demos. I'm sorry. We got some insurance issues. They told me if I can put some thread to tie my quadcopter to a table. I did this at home and smash it to the ground. So no, obviously I won't be able to do this. But I got videos. So this is the first one. Demonstrating the hijacking process. So I got a CX-10, so it's waiting for binding. I perform this binding with a remote controller, and I can control the drone with this remote. So this is quite okay. And then I'm using my rack transmitter. Well, basically this is not powered on, so it doesn't work. So I put power on it. Just check if the original transmitter is disconnected. So here it is. I got the control of the drone, and I'm going to use my my rack controller to pilot the drone. So this is quite interesting. So this was a test bed I made on my desk. And I made another video with showing the real flight. So this is quite the same. I just start the quadcopter, put it on the floor, binding the quadcopter with the remote controller. So here it is. So I can fly the drone with this legit remote controller. So I'm not a good drone pilot, you know. So as I said. So here it is, and then I take my rack controller, power it on, sorry. Just, oh, here it is. So I'm just checking it. Normally when you do it live, you get some trouble with the quadcopter, but if it's flying high, this is not really a problem. You can get the control quickly. So here it is, and using my rack controller, I was able to fly it smoothly, well, almost. Well, so it's working, and I can fly it. It's not just a proof of concept. So sometimes I get the remote controller disconnected, but I also experienced some issues with the green version of this quadcopter. I ordered some on Amazon and received them at home, and then when I tried this attack, it did not work very well because the sticks do not return the same values. So this is a problem when you are trying to take control of this. So hopefully everything is online now, as I'm speaking. So I put everything, the tools, the firmware, and so on. It's available on GitHub. It's open source. If you have a microbit, feel free to use it and test this firmware. If you find issues or the bugs or so on, file a pull request. If you test it, you will see that it's a child's play to hack into some things. So as a conclusion, because I got to be very quick, this is a cheap, tiny, and battery-powered radio frequency hacking tool. So this is quite interesting. It also allows rapid prototyping. If you are going to experiment some ESB protocol, SB protocol, or BLE, you can do nice stuff with it. It may be better than Basty's Modjack. I don't want to get Mark Newley angry, you know. And you can do even better with the Macrobits DAL, which is a device abstraction layer developed by the University of Lancaster. So this is a C++, not Python, so you have to get deeper in the source code. But I'm currently working on a start of implementation of Mike Ryan's hacking tool for BLE. So Mike Ryan's developed a BLE sniffer based on the Ubuntu using some SDR. And guess what? You can, I'm quite sure you can do the same with the microbit. I implemented the access address recovery, the CRC recovery from this tool. It's still in development. I got no proof of concept to show you, but if I connect my smartphone to a device, I am able to get all this value back and the op interval too. So it's just a matter of time to get it working with a real BLE device. So this is just some future work that comes with all of this. So if you have any questions, I will be available out there. Wandering in the halls and rooms. And thank you.